Okay. Well, good afternoon, everybody, and welcome to today's ASHRAE talk, and more importantly, welcome to Ermid Group. So for everybody here, we had a fantastic tour of the facilities here, which has been absolutely fantastic. Really welcome. My name is Howard Neville. I'm a mechanical department manager with BIS. And I'm also the technology transfer chair for ASHRAE Ireland chapter. We had a fantastic day for you here today. Dr. John McKeown will introduce you to the facilities here. Then we'll have Don Colliver, Vincent Sacreda, and Wei Sun will all be giving talks. I will over the computer over here. Doesn't work. Good question. Can everybody hear me online? Yes.
Yes.
That's great. Thank you. Thanks for letting us know. Yeah. It's working. Is it changing there? There we go. Okay. Right. Now that's great. Okay. And then move on. Okay, so we will have actually it says question. It says after each session, but we will actually do them at the end. So if you want to, if you do have questions as you go along, though, there's a chat function on screen. So if you want to just click on that, and you can put your questions in there. And if you're having any difficulties, just if you could ping Secretary in ASHRAE Ireland. Karen isn't isn't in the room, but she is online. We are recording this session, so if you do not consent to being recorded, unfortunately you can leave. That's your only other option. But for further information, please do go to ashraeireland.org webinar. Some of the previous webinars that we have done on there. So it's fantastic stuff on there. Please do continue the conversation afterwards. So you can join us on ashrae.org. Most importantly, join us as a member if you aren't already. Why aren't you? Please do be a member. You can volunteer for a committee role. We do have some upcoming events. Last week we had a fantastic Young Engineers Network events, and we launched our this year's mentoring program. If you want to click on that link, you probably can't click on the link there on screen, but if you go to the ashraeireland.org and you can click on that link, please do. So you can either join as a mentor or as a mentee. And the next big coming up is Mitchell Swan will be joining us in December, on the 3rd of December. We'll be talking about building outcomes and connecting green building outcomes to enterprise sustainability. That's a lot of words to say. How do we make cost and sustainability match? So that'll be an interesting talk. Okay, so first up would be John, Dr. John McKeown. So Dr. John McKeown is CEO of Allergy Standards and a medical doctor, but also a medical entrepreneur, I think is how I just describe. So probably Ireland's leading medical entrepreneur, and that I can't think of any others.
Leading entrepreneur.
Leading. There we go. So I'll hand you over to John.
Thank you, Howard. Appreciate that.
Thank you, John.
Thank you. And just do a quick sound check. If anybody could just put a thumbs up or in the chat there, and Dave here will let me know everybody can hear me. Quality of sound not very good, Dennis O'Neill. So I've moved the microphone closer to me. If somebody wants to put in the chat, that's all good. Okay, thanks. And thumbs up. Okay, thanks, Edith. And thanks, Emma. Appreciate that. All right, so I want to just set the scene a little bit. So again, welcome to Ireland, our distinguished lecturers. Thank you for coming here. Thank you for all the ASHRAE members who made it in person today. And what I want to set the scene is for what I describe the why of getting indoor air quality correct. Why is this really important? And then you're going to have the experts who are going to show you the how and the other integrated events of energy and our planet. But so what I'm going to talk about is the work we do in Ermid Health Group. Just to give people some bearings, we've got two offices. One of our offices is the main city centre, and we're out here in City West, and we've got a facility here which we just had the facility of. And we have a brand portfolio here based on the Indoor Air Innovation and Research, the iAir group, of which the AirMid research facility is one of those. And the very astute of you, and to our American guests, you may have seen this beautiful bridge in over the Liffey, the Calatrava Bridge or the Samuel Beckett Bridge, and that's what we use for our logo, because I think it's very important to bridge architects, construction professionals with healthcare professionals. We were talking about the importance of the indoor environment. And these are some of the brands. We do product R&D, we do government research, we do verification, we do certification on both sides of the Atlantic. But just to tell you my story about why is an emergency room doctor addressing the ASHRAE chapter group, my journey began with the connection between the indoor environment or the built environment with regards to kids with asthma and allergies. And the parents would ask me, how do I stay well, doctor, rather than having to come to the emergency room and you treating me when we become sick? And we all know, as ventilation professionals, we spend 80% of our time indoor. We're very familiar with the research about indoor air being more polluted than outdoor air quality. And if you're going to handle asthma and allergies, you need to deal with trigger factors in the indoor environment. And I would give the parents advice about what vacuum cleaners to buy, what pillows to buy, what cleaning products to use, how would they design their homes, how would they ventilate their homes. But they would get very confused, overwhelmed. And when we looked at the labeling that was out there, it was either based in good science, but very difficult to understand, or it was based in bad science, words like hypoallergenic and so forth. So we actually developed this certification program where we'll test consumer products. They'll come to a research facility like this. If they achieve our performance criteria or suitability criteria, we will award this certification mark. So if you're Irish, think of Guaranteed Irish, or look for the union label in America. And this means the product will actually help you improve your indoor environment, specifically avoiding indoor allergy triggers. So that's how I got started. And we will work with these companies all around the world, whether it's 3M or a Dyson or an LG, all big brands that use or make products targeted at improving the indoor environment, and they would have been tested here. And this is how we may do some of the activation in America. You can see an end cap in a retailer here with 3M furnace filters that are certified with dusting cloths, cleaning products, paint, and so forth. And that's how they'll go to market and activate. And we've done a lot within America. We got a congressional citation on helping underserved communities. A lot of our big brands would go to homes, remodel homes, donate products, do educational programs to impact on underserved communities on the asthma and allergy rates, and we've been recognized in the States for that. One of the reasons why we set up the Institute and the Bridge is that I spend a lot of time speaking at conventions around building professionals, brands talking about the indoor environment, around sensor technology, around healthy buildings. And I also spend a lot of time speaking to healthcare professionals talking about the exact same thing: sensor technology, wearables, keeping people out of hospitals, the role of the built environment. But the problem is they don't speak to each other. So the idea of our institute is to be that bridge, and it's a 501c6 based in DC, and its role is to produce research. It's like a think tank. Sorry, it's almost again. His role is to produce keynote research, and you would have seen some of these posters. There's some in the room around me. Here's Dr. Southey, who gave you a tour today. We're looking at
just mouse as a mouse mover on it.
Thank you, Dave. It's great to have the IT backup. Great. So nobody else can join now. So and so we publish thought-leading events. I think we had a good conversation down in the laboratory on UV technology. This is a paper that Angela did on novel UV testing. And we also have education. We think it's really important. If you're going to get serious around products and about buildings, you've got to educate professionals. That's why we're very happy to involve. So within the Institute, there's an academy, and it's recognized for all the CUs, whether it's the American Institute of Architects, American Society of Interior Design. So what I'd like to talk about is, as I said, the why. Why is indoor air quality something, and not only IAQ, IEQ, indoor environmental quality, really important? And the way we think about it here is we've broken it down to these big kind of 5 shifts in society. I'm going to go through these one by one. And I know, Don, you're going to talk a lot about, say, the planet aspect of it. So everybody's very much switched on about outdoor event. Even if you look at the the standards, the ASHRAE standards, they don't talk about fresh air anymore. We talk about clean air, equivalent clean air, outdoor air, because it may not always be clean or fresh. So whether it's adverse weather events, like let's say the hurricane in Miami recently, or the forest fires we've had in Europe, there's a big shift in the planet. There's a big shift in energy. There's a big shift in operational carbon. People are really aware of the person.
Somebody else seems to be letting me in, sorry.
Okay, so maybe Emma can let me, if you give Emma administrate. So this whole idea of buildings and the role they play in the planet, everybody needs to be switched on to this. So this is Matt Ellis from Measurables, a great slide he produced at the Building Owners and Managers Association meeting last year. You're looking at building construction, 10%, and then operational buildings. We spoke about at dinner, operational carbon. So this is something building managers, building owners, the asset owners, everybody needs to be switched on about this. The problem is that if we're all trying to decrease energy usage in our buildings, but because of the pandemic, we all want to improve indoor air quality. So there's a natural delta here, there's a challenge. And there's a tendency for people to think, well, if it's good for the planet, it's going to cost me more money. If it's good for people, oh, that sounds expensive. And what we need to do is kind of reframe this kind of conversation and say, no, the innovation, the delta there is the people who can figure out decreasing operational carbon, but actually having healthier buildings. And that's where the opportunity, I believe, will lie in the future. And we spoke a little bit about novel air cleaning technologies, low impedance air cleaning technologies, and is that the future? And we know as construction and building and ventilation professionals, these are all connected, there's trifectas. So as we saw in the first energy crisis back in the 70s, the EPA's own building, they tried to improve energy efficiency, but then they had outgassing and a VOC issue, and they got sick building syndrome. So you can't really touch one part of this trifecta without impacting on the others. So we need to know about how these are joined up. So that's one of the big shifts that have come. And I'm seeing this already. This is NACA, the National Association of Duct Cleaners Association. This is some work they presented at ISIAC in Honolulu. So this is the Trade Association for Duct Cleaning, and they're now switched on about energy efficiency and health outcomes. And they've done a lot of work with Mark Hernandez in Colorado around improving energy, improving health outcomes in schools by cleaning ducts. And the Steel Manufacturers Association are actually putting the ducts and then cleaning it. I recently gave a webinar with them as well. These guys are very much switched on. The industry needs to know about energy and health. The other one is this big shift is we're in a post-pandemic world. The reason I put this slide up is people may not realize the reason why today we say bless you when you sneeze is from the bubonic plague in London over 300 years ago. That started as a respiratory. The first symptoms were respiratory. So if you started sneezing, people knew you're on the way to this horrible death. The reason why I put this slide here is that the pandemic is behind us, but the cultural shift are going to maintain, but just like this one stayed for 300 years. Let's see, Wei and I, the only people in the room wearing neckties, that they've kind of gone now with the post-pandemic. So society has shifted and people now can join the dots about indoor air quality and health outcomes. But interestingly, again, this is not new. Benjamin Franklin was saying this about 300 years ago, and Florence Nightingale was saying this over 100 years ago. So it's now, I think, reached a threshold and a breakthrough point that society realizes indoor air quality, surface technology will impact on my health, and they're going to be asking for it going forward, whether it's in their schools or their workplaces or their churches or their homes. The other big shift is technology. So we had our lab tour today. We were seeing these kind of big bulky particle counters, VOC measurements, qPCR, big equipment that's heavy, costs $50,000. Then there's actually one on the windowsill behind us there. We're all very familiar with the ARANET CO2 monitor. This is me bringing it on an Aer Lingus flight. You see this on Twitter, people are doing this. So miniaturization of air quality, and ultimately it will be on our iPhones, and people will be able to walk in buildings and they'll be able to get a VOC reading or a CO2, which we all know is a proxy. And then there's even emerging technology where you can just breathe into a device and it can diagnose illness, it can diagnose health outcomes. So technology and air quality has really moved on as well. And the other big one is policy shifts. We're all members here of ASHRAE. ASHRAE, for the first time, the ASHRAE 241s changed standards. kind of a lot of this was triggered by the White House Indoor Air Quality Summit, which we, through our partners in America, participated in. That triggered the CDC, and they had their blank 5 air exchanges per hour. ASHRAE then came up with ASHRAE 241. AHAM have changed their standards. They have now microbial CADR, the National Association of Home Builders. I'm on the Healthy Home Subcommittee, and then the IEC now for the first time is having virus claims validated, and we're also on the IEC Air Cleaner Committee as well. So big policy shifts around this. And then if you just take a quick scan of looking throughout America, you have the Healthy Workplaces Coalition, that people are going to return to work. They're going to want to know that the indoor air quality is healthy, healthier schools, healthy and green schools, the American Society of Interior Design with the LEED, with the WELL building standard, all coming together around the idea of healthy and sustainable buildings. So people-friendly and planet-friendly buildings. And then the manager of the asset, a lot of the US economy is based on property, and the building owners and operators are worried about what they call stranded assets. So if you own a building asset that's been proven to be an unhealthy building, you aren't going to get your rental yield on that. So everybody's really switched on to healthy and energy efficient buildings. American Institute of Architects actually changed their constitution to say it's now part of an architect's duty to design a healthy building. That's quite a fundamental shift in their own constitution. So the way we think about it here, very plainly, is you have people who blueprint or design buildings, the American Institute of Architects, people who construct them, the National Association of Home Builders, interior design, American Society of Interior Design. Then you have the ventilation professionals, you've got the building owner and manager, you've got verifiers like International Well Building Institute, Wellness Within Your Walls, facilities management, the IFA, ISSA, and they all have a stakeholder in how do we get healthy people in the buildings. But as I said, the reason why we feel the role of the Institute is all these groups are having research, design, publications, but they're not speaking to each other and sharing their data. And we want to try, and that's part of our mission here, is to get these groups to speak to each other. So the other big shift in culture is this concept of well-being. We know, and I have a slide on it later on, that America, they're spending $4 trillion on their healthcare budget. 20% of their GDP is simply not sustainable. You can't be a competitive country in the world if you're a sick country, and if you're spending 20% of your GDP on sick people. And the way we think about it is the $4 trillion dollars is really spent down here on the red end. It's access to healthcare professionals and ER surgeons, family doctors, as it were. And it's kind of rescue medicine. It's what Dr. Gupta would say, heroically pulling people out of the fire rather than stopping people falling into the fire in the first place. And what people have realized is that if you keep going down here, whether it's a nurse, your family doctor, your physio, your exercise coach, your mindfulness coach, your nutritionist, the value and the return is going to be down the green end of the preventive end spectrum. And I believe companies like our own who are designing healthy products and verifying healthy products, but people like yourselves who are designing healthier buildings I'm not trying to turn you into doctors, but on this kind of wellness spectrum, we're on it. And if you design buildings or make buildings or ventilate buildings, you need to feel as yourself part of this conversation. And the $4 trillion we're spending down here will rebalance to this end of the spectrum going forward. And this is the data on it. This is a slide here. We had Jerome Adams at the Institute recently, the ex-US Surgeon General, and his slide was actually 90% of the healthcare budget in America is on access to doctors and molecules and more complicated treatment. But if you look at actually what influences the health outcomes, what we call the social determinants of health. Behavior and your environment makes up for over 70% of it. A very, very small amount of your healthcare budget goes into influencing this. And this is the way of the future, because the current model, again, this is Jerome Adams saying this, in America, you don't have a healthcare system, you have a sickness reimbursement program. And you're actually incentivized, hospital CEOs are actually incentivized and paid if they can fill their beds, not if they can get people out of their beds. And another example here, again, I applaud ASHRAE, not for accepting my paper, but the fact that they wanted to have a paper looking at how do we bridge health metrics, how can we join the dots between what we know we can do to a building to make it, inverted commas, healthier, and then we can measure that building to show what we've done is having an outcome. But what we can't do is show with a lot of research to date is people in healthier buildings have healthier outcomes. So this is a piece of a paper they asked me to commission looking at bridging health metrics. And I'm on the ASHRAE Environmental Health Committee, and we are looking at having unified metrics of harm and well-being within buildings. Okay, so for those who didn't have the physical tour today, I just want to flash through very quickly. We've got another 10 minutes to go, so I'm good on time, about what is the kind of research facilities we have here. So essentially what we've developed here is a series of aerobiology chambers that are surrounding a biosafety level 2 laboratory. So we have 10 chambers. I'll talk a little bit about now how we set them up. And then right in a kind of hub and spoke model, right at the center of the research facility, we have a virology lab, we have a mycology lab, an allergen lab. We can do VOCs and we can do particulars. And what's unique about what we can do here is we're not only biosafety level 2, is the proximity to the aerobiology chambers and the mixed degrees of specialist people we have here. So essentially, a chamber is going to be a climate controlled, double sealed, hermetically sealed chamber. It'll have an ante-room, it'll have air handling units to mass balance, to modify temperature, humidity. There was some good conversation about pascals and negative pressure and positive pressure. And then you will have ways of ports that you can actually add in various analytes of concern, whether through the high ports or low ports, depending on what you're trying to replicate. And then how you get it in is very interesting. We spoke today about whether you use nebulizers, whether you use dust introducers. So we have different pumps and methodologies for getting it in. And then once it's got the allergen of concern, or sorry, the contaminant of concern is within the chamber, how do you then analyze it? So you can actually use a glass impinger, you can use a dust impactor, you can have various particle countings, and you have other detective VOCs like the grey wolf and so forth in there. So build a controlled environment, punch holes in it so you can introduce contaminants in there, and then put in your monitoring equipment in there. And how you put things in and how you monitor it completely change depending on whether you're using a virus, an allergen, a bacteria, or a particulate. And then is what do you put in there? And there's various proprietary mixes we have in there. I put in there a virus, as we were speaking about earlier. Some people just put in a nebulized purified virus in there. But there's now research show if you don't actually put that in an artificial saliva, which is kind of as revolting as it sounds, it behaves completely differently. The respiratory droplet and also the ability, for example, for UV light to kill a virus when it's within a salivary droplet is completely different to when you put it in just as a purified. Okay, and then I said, once we conduct the samples, we can bring them straight across to the lab. So essentially, and the people who have had the tour here today, this is one of the chambers you would have seen. That's what we've got. You've got a climate controlled chamber, air handling units on the top. You have an ASHRAE 52 duct wrapping it around, and then you'll see the various ports to introduce the various dusts and so forth. This is the type of equipment we'd have in our research chambers here, qPCR, so we can actually put in very, very small amounts of viruses. We had a good conversation about toilet plumes and in washrooms when we're washing hands, whether it's in a hospital or an ICU room, immunocompromised patients, you need to track and trace very, very small amounts of viruses in the air. And you need very complicated machinery like a qPCR, because you can't really culture these or do a plaque assay. So we would have all this type of equipment there in the laboratory once we generate the samples. And this is the type of research we will do with regards to claim verification, research testing, field studies, looking at novel technologies, whether it's for viruses or allergens. And these are the type of clients we have. So I'll just kind of go through a couple of quick 3 case studies of work we've done with clients. One study we did, and we published this actually in a medical journal, Dyson came to us and they wanted to produce data about do the hand dryers, which will blow air, and they obviously have a suction component as well. Are they themselves contributing. If you put something over a sink here and there's bacterial contamination in the sink water from the last person who washed their hands, if you come in and dry your hands with this type of equipment, what's happening within the environment. So you can see the technician here, he's inside one of those chambers that I showed you. And he's wearing a sensor technology here. You see the little pump on his back, and he's also connected to a fixed sampler here. And as we're introducing bacteria or viruses or mold, we're washing our hands and we're seeing through these particle counters what's getting into the breathing zone at different levels. And then you can enhance the study by saying, well, let's put some germicidal UV downlighters, or let's put a germicidal UV downlighter onto the sink, or let's put in an antimicrobial coating on the sink. So now you've got antimicrobial, or you've got a resistant bacteria. We spoke about something like a C. diff. What if we enter in the cleaning protocols? So put in some C. diff, have a cleaning protocol, use it. So this scenario analysis, we're looking at cleaning protocols, cleaning SOPs, and ventilation strategies. What's the actual impact on, say, a patient lying in a bed 3 feet away from the sink? So that's the type of research we do here as well. Alstom, a big European train company. Those of you who are Irish will recognise this as the next generation of DART that's coming to Ireland soon. And we have the team from Alstom out here. This is a novel air handling unit they're going to put on top of the trains. They're putting in, again, some germicidal UV. They're looking at some other novel air cleaning technologies. And we can do a customised rig and actually build a rig of the train. We can't drive a whole train into our chambers, but we can certainly build a rig of the train in a chamber, set it up, and then we can actually convey the experiment. They can commission the experiment. And many of our clients actually come over here and they'll help set up themselves, and they'll rent a chamber for a couple of days as they're assessing their technologies. And the last one before I finish up is Philips. Philips designed a new protocol, some novel technology of, this was actually pre-pandemic, the coronavirus pandemic. This was Haemophilus influenza, so H1N1. And they, again, you'll see in the chamber, the device is in there. We're nebulizing in the glass tubes here at the front. We're nebulizing virus into the chamber. We're mixing it, getting a good high concentration, and presenting the data against the control. You will see a lot of marketing literature where they're showing virus decay curves, but often it's to something that will happen if you nebulize a virus in, it'll dry out, it'll fall to the ground, and you'll get this sense that you're actually removing virus, but you're not, it's just natural decay. So we'll put this in here and run control runs, which again is very difficult to do because you've got to get very, very small quantities of virus picked up in your qPCR. But it gives meaningful data that really good brand companies will then stand behind this, as will, say, retailers and Amazon. Big retailers, big brands like an Amazon won't touch a virus claim unless it's been done in a laboratory such as ours. So that's pretty much it. I just want to finish with a couple of things that may be of interest to the group. One program we are involved in is in America. It's called ARPA-H. They're putting about $1 trillion into this. So in America, they had DARPA, which is the Defense Advanced Research Program. Now they have an Advanced Research Program for health. And within that, they've carved out a few areas. There's precision cancer, there's care of the elderly, but healthy buildings is one that they've actually designated within that. So it's called BREATHE, Building Resilient Environments for Air and Total Health. They're looking at ventilation strategies, they're looking at novel air cleaning technology, they're looking at real-time sensors, and we're within 2 of those programs. And this is something I think the audience here should be aware of. There's a huge amount of investment going to go into this program. And some of the other work, again, just to put it on the radar of the audience. We were speaking about Bill Banfleth earlier. Bill and I, and I think this is a good slide. It's a coming together of, say, our research institute, the US Green Building Council, an ASHRAE thought leader like Bill Banfleth, and then the International Well Building Institute. And this was a webinar run by the National Institute of Building Sciences. And again, it just shows the coalescing around ventilation strategies, healthy buildings, planet-friendly buildings, and people-friendly buildings. And this is the type of the work that we're involved in, and I think the ASHRAE Ireland folks should know about. So just to finish up, what we're trying to establish here is we believe, as I showed you those 5 fundamental shifts, there's been a big paradigm shift in the air-aware consumer. In the old days, particularly in Ireland, we would call it air, don't care, open a window, I'm not going to pay for air, air is what we have. And stealing a line of Dr. Lee, who said, look, if you're walking down Fifth Avenue and somebody gave you a glass of water, just, oh, here's a glass of water, you wouldn't drink that. But we're all expected to share air. We live in shared air. And just as we don't eat food off contaminated plates, we don't drink contaminated water, there is this paradigm shift that air is really important. So we're trying to wrap around that fundamental society shift. A research institute, testing, consulting, verification, and you saw the technical facility downstairs, certification with like the work we're doing with the Asthma Allergy Foundation, and then the work, as I said, we're an accredited educator by the American Institute of Architects, for example. So that's what we're doing here. We're delighted to be part of the chapter group, and hopefully I've teed it up now on the why indoor air quality is very important. So Howard, I'll hand back to you for the experts about how you actually get it done.
Very good job. And we're very much going to hand over to the experts. First up, we have some ASHRAE royalty. We have Professor Don Colliver. So Don is the Professor of Biosystems Engineering.
Yes.
Okay, great stuff. ASHRAE President from 2002, 2003. And yes, you can okay, that's yep, we get there anyway. I think as part of that was launched the ASHRAE energy design guides out of that. So I'll hand you over to Don. Thank you very much.
Well, first of all, thank you very much for being here. There is no ASHRAE royalty, by the way. I think the ASHRAE royalty are those that are sitting in this room, and the royalty means that you're trying to improve, and thus you're the ones that should be. So this is part of the ASHRAE Distinguished Lecturer Program, which is a program within society where they will sponsor folks to come out and speak to the individual chapters. So certainly I appreciate the opportunity to be here. Thank you for your invitation to view this lab and for the opportunity to be with you. John showed a picture of President Dennis Knight, the current ASHRAE president. I spoke to him a couple of weeks ago. And Dennis said, make sure that I bring greetings from him to the chapter. So certainly I do express my appreciation. Is it me?
Just online, they're not seeing the.
Okay, so anyway, Dennis did express appreciation for all members who participate in society activities, not only the members, but those who are affiliated with our industry. So that, as was mentioned earlier, it is everybody working together as a team is what we're trying to do, is to build a better world that we can all live in. So with that disclaimer, which I don't know what happened there.
That's pretty green.
That is pretty green, but that was on a slide that I was prepared for. So, okay, so what I'm going to be talking about is one of the factors that impacts, and it's kind of a bigger picture of what we're doing in this industry. And it has to do with decarbonization. And what we'll first talk about is how are we looking at decarbonization? What are some of the parameters? What are some of the things that we deal with that impact what's going on in this world now and what's going to be happening in the future? So with that, and then also I'll make a short introduction into what can we actually do in clean rooms. So as we move forward, and this is probably you are very familiar with this, but our global temperature change has greatly increased over the last few years. When I say the last few years, in modern times, we're talking about in the last 2,000 years. The center line here is what the average temperature was per decade over the last 2,000 years, and it's based upon zero temperature for the industrial age. Okay, so then if we look at it, since our industrial age has started, you can see how our temperature has increased. If we look at it then further, okay, so as we look at it further, we see that today, if we compare it to what the temperature was for the last 100,000 years, we see that it is greater than it has been in the last 100,000 years. What's the moral of this story? Our climate change is real. So what can we do about it? What should we be doing about it? So, you know, if we look at it in temperature, one of the major things that is driving that is looking at an energy balance. Okay, let me ask, how many of you are engineers? Okay, went to engineering school, went to whatever education you had. So as a professor, when I as a student, if they don't know the answer to the question, there are two questions you need to be thinking about. A, an energy balance, and B, a mass balance. And for those of you that are in this industry, you understand what those two important things mean. So if we have more energy in than more energy out, our world is out of balance. In order for us to be in balance, and you know, we've got to be in balance, what happens is we've got to have some energy storage, and that is temperature rise. Now, weather around the world is dictated by the oceans. Ocean temperatures are really what drive our weather conditions. And a couple of years ago, there was a group that put together some analysis that said, let's look at the temperatures in the world. What they found was that the amount of heat that was trapped in just the year 2022, the amount of heat that was trapped was 10.9 times 10 to the 21st joules per year. Okay, think about that for a second. Who can visualize anything to the 21st power? Okay, when we talk about sizes, you're getting down to how many zeros past the decimal point are we looking at some of the particles we're looking at? How small is that? Some of the particles.
2.5. Many zeros.
How many zeros there?
10 to the minus 4.
10 to the minus 4, okay. 4 zeros. Here we're talking about 21 zeros. Okay. Well, Culver's people, Brian, mine can't think about that. So I says, okay, let's back it up to a single second. Still 10 to the 14th. I can understand that. We're talking about temperature driving the ocean temperature is driving it. But let's say, okay, how much heat was required to do that? Well, so I says, okay, what type of thing? What's a big source of energy? What's a big source of energy? Instantaneous energy. What can you think about on that? Nuclear. A nuclear bomb, for instance. So if we look at it, I heard a laugh. Who laughed? Right?
We said the sun.
You said the sun. Okay, well, yes. And there are variations in the solar radiation, but that is far less than what this is. So if we look at it, the Hiroshima bomb is 6.7 to 10 to the 13th joule per bomb. So the question is, how many bombs did it take? What's the equivalent amount of energy in nuclear bombs did it take to increase the water temperature in 1 year? 5 Hiroshima bombs going off every second through the entire year. 5 Hiroshima bombs going off every second. That is how much energy is being added to our Earth's climate. So, I don't know about y'all, but that kind of puts cold chill bumps on my spine. So, what can we do? John showed this picture earlier. What can we do? Well, buildings are massive medicine for the Earth's fever that we're seeing. Buildings are roughly 37% of the energy-related CO2 emissions in the world. So what can we do impacting the buildings. Well, what can we do to reduce the carbon? And I've got a whole different lecture that's talking about why is temperature rising and all that, but I think you've all heard the stories that CO2. So how do we reduce the carbon output? Well, first of all, we decarbonize. And just to get us all on the same level here, we're talking about the reduction or elimination of greenhouse gas using the standard metric of carbon dioxide. Now, one of the things that we think about, or we should be thinking about, is for building decarbonization, we need to think about whole life carbon. Most of the time we talk about operational carbon. That is the carbon that is being produced by our electrical utility that is burning whatever fuel it is to produce the electrons that are used in our lights or heating or whatever. Embodied carbon is just as critical to us. And that's something that we'll be addressing here in a minute. And it comes into play when we're talking here about clean rooms as well. So let's look at what some of building decarbonization. Let's look at kind of what are some of the basics of this. First of all, let's look at the foundation, energy efficiency. The number one thing that we can do is energy efficient. The second is switching to cleaner fuels. So let's first make our facilities more energy efficient. Then let's switch to those fuels that are cleaner. Here we're talking about typically a transition from electricity to natural gas is one of the, from natural gas to electricity is one of the things that we're talking about here. And then finally, using low or no carbon fuels. That is, let's make our electricity from renewable energy resources. So that's kind of what our basics of our foundation are, but let's look at what some now of our pillars are. The first pillar is talking about the envelope. Let's first of all reduce the size of our space that we have to clean up. And that has a couple of functions. First of all, it reduces the required airflow, energy to heat and cool, smaller systems. Both of those impact both the embodied and the operational carbon. So let's right size our systems. Let's make them, first of all, many times when we get into the design parameters, you'll have the designers have one spec and then the next person says, okay, I understand that. Let's have a little bit of margin of safety. So I'll add something to that. And the next person will add something to that. And at the end, you are not right size. You have a multiple of double, for instance. So let's right size it. Let's agree on what the design loads and so forth are. Let's upsize things. Let's use variable frequency drives, operational safety, operational savings, and Way and others will talk about this later. There are a number of different things that we can do. As far as clean rooms are concerned, we're seeing that those are having a energy usage index that is many times greater than our traditional office building. 30, 50 times as great as what our traditional office building is. And if we look at that, our HVAC systems are about 80% of what that is. So that's the first one. Our energy efficiency is their second one. Then if we reduce the total airflow, we can greatly increase our energy efficiency. Let's use efficiency and heat pumps. And people are saying, well, it probably is inappropriate for this group because y'all don't get into the really cold temperatures. But just last week, the US EPA, or US DOE, said that they were seeing several of the manufacturers now have heat pumps that are viable all the way down to 0 degrees Fahrenheit. Typically, we're seeing heat pumps that were down to about 0 C. Now we're seeing heat pumps that are good all the way down to a much lower temperature. Decreasing the pressure drop across our system using VFDs, controls, all these are important characteristics dealing with energy efficiency. However, this is one of our keys. Never forget that contaminants are going to be our criterion that we have to deal with. We can't reduce, or we can't make things so energy efficient that they don't work to reduce our contaminants. So that's kind of one of those underlying principles that we must not forget. The other component dealing with energy efficiency, and I think it's important for us to realize, for those of you who were back in physics or in fluids, that we have fan affinity laws. In essence, what that says is if we can reduce our airflow by 20%, we're going to reduce our energy usage by about half. Okay. Reducing airflow is a critical component to us, and it's very easy to do. So that's one thing. The other is minimizing the pressure drop. And remember that our pressure drop is proportional to the phase velocity squared. So in essence, if we take I'm an American, imperial units still in my background. If we take a 12-inch duct and increase it to a 16-inch duct, we can reduce our pressure drop by about 75%. And that's just the natural laws of airflow. So what our take-home message? Use bigger ductwork, lower the face velocity of our air handling units, lower the face velocity of our filters. We can greatly reduce the energy that's required to do that. All of this, reduce fan motors, size, VFDs, electrical hardware requirements. So if we're talking about decarbonization, saying, okay, it's going to cost a whole lot more, the component is if we use the right techniques, we can actually reduce the cost. And I've got some friends that are designing extensive office buildings, and they're actually costing less than what they were doing before they were using some of the techniques that we're talking about. Oops. So embodied carbon. This is, and I may be speaking to the choir here or preaching to the choir here, but if we look at the third pillar of decarbonization, we're talking about embodied carbon. And I know that Europe is much greater advanced than the US and much of the rest of the world talking about embodied carbon. But what we need to remember is as we reduce the operational carbon, what's happening is the proportion of the total carbon then that's involved in embodied carbon becomes much more critical to us. It becomes something that we need to be more important about. So what we do need to do is remember that decarbonization is both embodied and operational carbon. And sometimes it can amount to as much as 2/3 of our total building life cycle carbon. So remember, if we're talking about the life cycle of a building, the embodied carbon takes it from what's it take to extract the raw material for the steel here, then transport that raw material to the factory, to manufacture, and then transport that to the site, and then construct the building. That's the product and construction phase of embodied carbon. Then we have the operational carbon, which is what's the energy that's used within the building itself. Not only energy, but I'll look in a minute in that we also say in the use part, we have some embodied carbon in the refrigerant that's used in our buildings. Okay. And then finally, what happens is we need to look at what's the end of life. What is our circular use of carbon? And that all of those are included in this the standard that you see here. So if we look at operational carbon, well, what happens is that we have here the decrease, or the operational carbon is here in blue, and the embodied carbon, and then after, some point in time later, you're going to renovate your building, you have more embodied carbon, and then finally you've got the deconstruction. Okay, a quiz. I'm a professor, okay? I love quizzing. Y'all don't. Okay, question for you. Why do you see the operational carbon decreasing over time? Why do you think this operational carbon is decreasing over time? Hello?
Renewable energy using more.
What exactly, what is happening is that our energy use to operate our building is coming from renewable energy sources. So therefore, we do not have as much operational carbon. What's that telling you? Our embodied carbon becomes more important to us as we have reductions in operational carbon.
It's assumed to be linear rather than at some point somebody would, new plants come on or new technologies come online. We don't know those. We can't tell the future.
I'm assuming this is linear. We can get into a whole discussion because I'm working with one of the largest utilities in the US, looking to see what is their generation mix for the next 30 years. As a side note, the cheapest electrical generation technique in America now is solar. So, but yeah, I've got it linear simply because it's easier to draw that.
That's what the question is. Going back, was it linear?
Pardon?
Moving backwards, so say between 2024 and say 1994, was it linear, or what did it do that?
Let's put that in the parking lot. Let's put that in the parking lot. We'll talk about it at the end here because your clock is telling me I need to move on. Okay, whole building life cycle EPDs. Your products in Europe, you're seeing those come forward. We need this applied around the world because this is a vast need for us. And the products that you're testing, do they have EPDs on them?
Yes, they will do.
They do?
Yeah.
Okay, great. That's one of the problems that we are having in America because those are not there. Okay. Reduce the loads is our fourth pillar. Using low carbon energy. Heating, water heating, cooking, heat pumps, surface water heating. The other is what we need to make sure though is as we switch to a different fuel, a different type of fuel, let's say for instance, I'm switching from natural gas to electricity in the building. Well, if your electricity is generated by a high carbon source, you actually are doing the wrong thing. You're reducing. So you need to take that into impact as well. Waste energy. We're seeing that a lot of companies now are coming in and they are using boiler exhaust, capturing the energy from the boiler, gray water heat pumps. There is a residential facility in New Jersey where what they're doing is, everybody takes hot showers. You've got all this hot water coming out in the gray water. They're actually running that through a heat exchanger heat pump, reusing that energy. So refrigerants, and this is one of those that is critical to us as well. Select lower global warming potential refrigerants, but it's these next series of bullets, the fugitive emissions, is what a lot of people are not thinking about. Maintaining the efficiency and using the refrigerants appropriately. Was working with one group and they were actually using the refrigerant. The refrigerant is a great cleaner, right? And so what they were doing was they were using refrigerants to clean the oil off of their tools. Okay, so this comes back to that bullet there where we're talking about refrigerant type and the leakage. So this is a graphic where what we're doing is showing the 15 years of use, what is per kilogram of CO2 that's in our system. Based upon what refrigerant it is and what the leakage rate is, you can see that from here you can draw the conclusion that your leakage rate can greatly impact the CO2 the CO2 equivalent usage of the building. Residential systems typically are in the 2 to 5%. Whoops. Residential systems are typically in the 2 to 5% leakage rate, and this is for 15 years. And I'm saying 15 years because we will be redoing a system typically after that. But so a commercial condensing unit, which is where you have a lot of built-up refrigeration system, where you've got a lot of piping in the construction, on the site, brazing and so forth, it's not uncommon to have 15% leakage. So R14 or 410A. That's going to be eliminated here soon. 134. But then some of these other refrigerants still can greatly, the leakage rate can greatly impact the amount of carbon that has been produced in your refrigeration system. Now, and we were just in Athens, and I was talking to a chap there, and he was saying that his refrigeration system, or a common leakage rate for the refrigeration system, was 30% for a built-up system. What we're talking about here is greatly impacting what the overall carbon of the building is. So especially when we're talking about clean rooms and other areas that are confined spaces, we need to really remember that leakage rate and good construction maintenance is critical to this. Finally, demand management is our seventh component of our pillars. Software integration is one of those keys that many of us kind of forget, but it is very, very important to us. Way's going to talk about this later on, talking about as we talk about clean rooms, can we change how the amount of air circulation in our facility is? And there are various ways of doing this, and Way, I'm not going to steal your thunder on that. So when we're talking about building decarbonization, you know, it's kind of been a downer, but yet there are some real challenges before us, but yet we have some great opportunities for us. First of all, we must realize that money does matter. We are being able to address some of the economics and addressing them aggressively. What is scalable for one system is not the same for a residential system. It's not going to be the same as what this building is. So we must keep in mind where our building scales are. The grid infrastructure is important to us. Our utilities are addressing this. I was at an IEA closed door session on energy security about a month ago in Paris. This was a very key component in discussion of that, of being able, is our utility infrastructure going to be capable to use it? The fellow next to me was the main electrical guy from Ukraine. Obviously, he had a different impact of this than the rest of us did. Cold climates, global warming. As we see global warming, we're going to have more air conditioning being used. Thus, we're going to have more demand for utilities. Retrofits is that big elephant in the room. We still need to be addressing that, and we are doing as well. So let's top it off. Well, first of all, we need to have the commitment. We need to create a culture. And with that culture, we need collaboration. We need folks like you in this room from the various aspects of the building community, the indoor environment community. We need to create a culture of collaboration where we design, plan, construct. All of those are critical to us. And finally, we need leadership. You are the leaders that are going to pull this together. We need champions for this. We need individuals and organizations that have the vision and the technical know-how, those with passion, persistence, and powers of persuasion. What I have found is that ASHRAE membership has the capability for taking on the leadership, and it is a challenge for us as well. So with that, questions or comments? I guess we'll do this later.
We'll do the questions later. I'll jump up and just one line. Don, thank you very, very much. Losing power, are we? Okay.
No, just making sure we're not going to.
Great stuff. You're almost in. Okay, so our next speaker, Vincent Sacrida. Vincent has over 40 years of experience in
42.
42. Okay, right. in his capacity in ASHRAE, you're a member of TC 911. Chairman of, thank you very much, and co-author of the Handbook on Clean Spaces. You are on the committee of ISO 14644.
Yep.
Thank you. And author in the ASHRAE Journal and engineered systems as well, as well as many, many other things. So I'll hand you over to Vincent. Thank you.
Thank you. Got my timer.
Nope, there you go.
Always looking at time, but here we go. Well, good afternoon.
Yeah.
I do appreciate everybody coming here. Which way's forward, which way's back?
This little button here, that's the one there pointing over there. Yeah.
So they go forward.
That's it, yeah. There you go.
Awesome. All right, learning objectives. So gain a basic understanding of variable airflow for clean rooms. Learn different types of particulate monitoring systems that are out there. Be able to determine space. Get the third one. So we're going to get into a little bit of that. So anyways, I'll go through that for a time. There's me on that particular job. I was actually doing a 1.6 million square foot facility for Boeing out in Washington, as far as for producing the 777X fiber composite wing, which was a fairly large clean room actually. Just as far as ASHRAE, being chair of the 9/11 committee, we do have our meeting coming up in Orlando, Florida. If you can't attend, it will be a virtual meeting. So if you're interested in attending that virtually, love to have you attend our meeting on that. So just to let you know that. So where are the savings? Why would we want to vary airflow in the clean room? Because it's tough enough just to get a clean room set up with the proper airflow, and especially the differential pressure relationship between spaces. It takes a lot of effort. But I want to show you here, which is the, excuse me real quick, what's the,
Which one?
the
green.
Oh, there we go. So anyways, thank you. Should ask beforehand. Anyway, so when you look at typical particulate in the clean room, and I've actually done this, and this is quite fascinating, is I could tell you when people enter the clean room, I can tell you when they're working in the clean room, and I can tell you when they leave the clean room. And here's a good example. So it's during the night, you got a certain particulate level with the airflow that you design for. And always when you design your airflow, you're always designing for worst conditions. And that's what we design for. But the reality is 99% of the time, you're never at worst conditions. Sort of like when we design for air conditioning and heating, you design at 1%. Well, that means is that 99% of the time that the conditions are you're not going to be operating there. So it's important to be able to control your systems operate at the level that's needed. So anyways, you look at this, you come in, the work group comes in, they're working. So you have a high, your higher level working level. Let's go for break. Lunchtime, afternoon break, go home for the day, and this is the evening. So this would be a typical shift. And for the most part, you're going to see that if you do particulate measurement in clean room, it's going to be some random variable of this. So that's what you're looking at. All right, so let's look, where's the energy used in the clean room, because that's important. So process, we say about 9%, where your heating and cooling water systems are going to be about 37%. The biggest single item you have there is your fans, because you got a high static pressure. For example, I'm working on the Lilly project right now. We have system pressures, supply side upwards of 8-9 inches, and we have some returns that are 5 to 7 inches. Pretty high static pressures. Those are inches water gauge. I'm sorry, I don't know the equivalent in pascals off the top of my head, but very high because we have a lot of HEPA filters, and we're dealing with containment of components during the operation. So we got a lot of safety measures. All right, so let's look at savings, because the thing is, this is sort of like, oh, why would I do this? What's the cost of doing it? What am I really truly saving? Now, I did update this with your electrical rates that I saw, which were quite interesting compared to the United States. About 38 cents a kilowatt hour. United States, it goes anywhere from 2 cents a kilowatt hour to about, 10 normally, unless you're like in New York or some other, because it's almost as close as yours. So looking at this, so the example I have is the 93 cubic meter facility, ISO 5, basically 125 standard 600 by 1200 millimeter HEPA filters. And so resulting in 137,620 cubic meters an hour of supply airflow, just to give you a feel. Now, basically airflow is 1.74 kilopascals, and I put horsepower, brake horsepower is 136. So for this example, we're also looking at, we're going to reduce the airflow 50%, 70% of the time. And we've got electrical costs, HEPA filter life, and a replacement cost. So let's look at it. So using the affinity laws, and Don, thank you for mentioning those earlier. We're going to do some calculations on that to determine, okay, if I reduce the airflow 50%, well, what happens to my static pressure? So we ended up, our static pressure will drop substantially, and we'll go down to only 435 pascals. And so quite a substantial drop. How about our brake horsepower? We go down again. It's a cubic function. We go down. Oops, sorry about that. If I can, there we go. When you look at it, we go down to 17 from 136. That's quite a drop in your power requirements. All right, so we have a reduction. We save 88.7 kilowatts as far as for that during that partial flow operation. It saves you a little over 500,000 kilowatt hours a year. And at 38 cents a kilowatt hour, that's $206,000 that you're saving. And then we're talking about a 93 cubic every square meter place, and that's it. So if you have a lot of spaces in your clean room, you can imagine how much money you're going to save. So euros is about 189,000. There we go. So as far as HEPA filters, heard lives of 5 years. Know of NASA, they actually have HEPA filters that have been in for 30 years. One of the people that Wei and I are on the NEB Clean Room Performance Testing Standard Committee. Wei's actually in the chair. And one of our members on that committee works for NASA. And they actually did a study on these HEPA filters. It's one, is there any degradation to the filter media, the urethane is holding it in or anything? And they found out they were in great shape. So HEPA filters, if you put proper filtration for them, will literally last forever. So looking at it in regards, and again, Don, thank you for the mass part, because this is how I did it, but it's by mass. As far as the life of a HEPA filter extended, say if you did have what normally would be replaced after 5 years due to static pressure differential, you can extend the life of your HEPA filter by 50%. That's nothing to sneeze at, especially if you have a lot of them at cost. All right, so you got to verify that you need to do this, the variable airflow, and do the modulation of it, because there's a lot of things that can be impedances to that. Your thermal load, you have a process that has a high heat load, you may not be able to do it. If you have a high process exhaust load, a good example of that would be a wafer fab facility. I did an Intel wafer fab facility last year, and we had 1 million, well, CFM wise, 1,200,000 CFM exhaust in the wafer fab facility. That really limited any sort of variable airflow in there. It helps. requirements as far as you have anything as far as LEL, lower explosion limits, lower flammability limits. That's what I'm facing right now on the Eli Lilly project I'm working on. We got spaces. I have a consultant who basically we're working with as far as to make sure we have proper supply airflow in there so we don't blow the building up. Actually, the building is designed to blow up, by the way. We have a blast wall in the north side of the building is designed if the reactors get away from us, they'll blow the wall out. Regulatory requirements. There are regulatory groups, FDA, other groups are going to require you to have a minimum air change rate. You may not be able to have variable airflow. Your airflow is based on exfiltration. If you have to I look at air clean rooms as a balloon. If I have to keep pumping air in because I have to exfiltrate all the air out of that space in order to maintain the proper pressure differential relationship to the other spaces, you're not going to be able to have variable airflow. Uneconomical. We're going to get into the economics here. I got an example. I did an example for it to show you where I think variable airflow is a really great idea, and there's some areas it's probably not such a good idea. Okay, so one pressurization relationship. So we want to have an understanding the different ways that we can control this space pressurization. So there's the pressure differential where you actually measure having two sensors across a differential pressure sensor, you're measuring across two rooms, and you vary airflow to maintain that. Volumetric offset is where you set it up, where you have airflow sensors, and the airflow sensor, you maintain a volumetric offset. And then a hybrid, which is one I usually use, is I have the volumetric offset, but I'm measuring differential pressures. And over time, I will adjust the airflow differential based upon what as the space becomes leakier or someone changes something out, that will do that. So let's look at that. Pressure differential, as I was saying, is you have a differential sensor and you have your supply airs, obviously, in this particular case, is being controlled by a particle monitoring system. And then the differential pressure, your return is actually varying to maintain differentials. So that's on that one. Volumetric offset. You basically have airflow measuring stations, and basically you, on your upfront test and air balance, you set up what that airflow needs to be based upon stable operations. Just to give you a quick idea, this is actually from the Eli Lilly project. I made sure it's pretty neutral as far as information, because I do have to protect client privacy on this particular one. But the main purpose I was trying to show here is this unit's a set and forget. We're going to talk more about set and forgets and what you need to do. Their requirements are we just basically have stable airflow. It's a set and forget. So there's no armatures or anything on that. So the test and balance form comes up, he sets up that Venturi valve and walks away, and that's all we do. So it's pretty straightforward. So design philosophies. If you're thinking about implementing this, what do you have to have in your mind as far as looking at it? Do not have two more spaces being served by the same control valves, because what ends up happening is if you start making an adjustment to one space, you're going to lose pressurization in the space, the relationship in the other space. So it's going to have to be pretty intensive as far as control. Each room has to have its own supply, its own return. Modules have the same performance characteristics. That's real important. And that's really tough when you come to supply and return, because if you have supply coming in and you have a lot of air exfiltrating, you're only returning a portion of that airflow, what ends up happening is your return damper is going to be smaller than your supply damper. So you have to make sure that the rate of modulation and operating characteristics are the same. One thing you also got to look at on that is what we call damper authority. Does everybody understand what damper authority is? No? Damper authority is the percentage that the damper being fully open's pressure drop in relationship to the overall system pressure drop. Typically for like a parallel blade damper, you're probably going to have as a linear possible on a parallel blade damper, it's going to be 20 to 30%. That's pretty high. For an opposed blade damper, it's going to be in the range of 5 to 15%. Just so if you hear that word damper authority, that's why it's important. If you have an air handling serving dedicated space, that Intel wafer fab facility did, we actually had 1,200,000 CFM air handling serving one space. So yeah, you can have it. In that particular case, you're not using dampers, you're using variable frequency drives to ramp up your fans up and down together. At that point, then you'll have to tune or modulate the supply and return fans up and down together with that. Typically, for multi-space, you're going to maintain your ductwork static pressures as well. So let's look at particle monitoring systems. There's continuous monitoring, and then there is the sequential particle monitoring system. Continuous, basically, you have as a group of sensors that you put in the space, and I always call it the hockey pucks. And you basically put them on like a workstation, your most sensitive areas in the clean room, and also other areas where you think you might get transgressions into the space. For example, doors, pass-throughs. If you have an opening in it for like a fill line or something like that in pharmaceuticals, those are areas that you would want to think about putting sensors in there as well. Typically, you're going to have the sensors, and you have to have a vacuum, so you can have a vacuum pump. Typically, these have 1 CFM draw per sensor, so think about that as well as what you're drawing out of there for sampling, depending on the number. So, oh, what did I do? This is a sample of what it looks like as far as physical equipment. I always like that picture. So that gives you a feel for as far as what it looks like. Hopefully everything's blurred out enough you can't really see whose it is. Sequential's different. Sequential, instead of having this monitor in the space, you have tubing going out and you're collecting the air and it's being brought in to a central location, the sequencer right here. And then it's basically going in and it goes into the particle monitoring. So it's a different philosophy. Now, the disadvantage of this is that depending on how many points you're picking up in a room, it could be 20, 30 minutes before you go back to that first point again. So you have to keep that in mind, because you got to realize is when it draws in, first it sort of purges the line, and then it senses it before it rolls on to the next one. So just be advised on that. And actually, we'll get a little further into that in the future. Sampling locations. The old criteria was a square root. If you take your clean room in square meters, take the square root of that, and that's the number of sensors. ISO 14644 has revised, and it's a much more prescriptive. Here's the table. And as you can see, I have the values in there for square meters and cubic meters in the table and the number of sensors. Now understand this is for initial setup of the clean room. This to certify it. This is initial. This is not, you continuously do that point. Am I correct on that, Connor? Yes, thank you. So what you do after that is that's where you determine, as I was saying before, with your client, how many locations do you want to have in the space, the clean room, in order for operation. So as you can see, you can get quite a few sensor locations. I think it's a little overburdening, but that was what is agreed to. Okay, again, locations, primary should be where your sensitive workstations, that's what you're there to protect. It's a fill line, you want to be next to the fill line. If it's somebody working with something on a board, say electronics or something, you want a sensor there. Wherever the most sensitive spots in that clean room. Secondary, again, doors, any sort of openings, anywhere you anticipate you're going to get potentially get contamination. Airflow devices, control devices, you want as accurate as you can. Typically, I use Venturi valves. If you can't use Venturi valves, go with opposed blade dampers. Those are typically you want as much as possible. Hopefully, they can be pressure independent so that any variability in the main is not affecting the operation of the dampers. You also want to make sure that everything you select as far as dampers and anything else in the system is non-shedding, doesn't create particulate. You also want it where it doesn't maybe absorb any contaminant and then re-release it. So you want to make sure you don't have that as well. You don't want, depending upon your environment, you don't want to have any corrosion. And you want an actuator that you can actually have a modulating rate or a modulating rate of modulation. So one thing as far as sequence of operations, you get into this as far as how often should this thing be continuous where it's constantly going up and down, modulating continuously? I don't recommend that, and I'll tell you why. Because if that one's modulating, how about the adjoining clean room? It's modulating as well, and you're not going to maintain that pressure differential dead nuts all the time. So my recommendation is modulate that room. The adjoining rooms are not modulating. Once that room's done, then you go around sequentially with your sequential counter to basically go from room to room to room and then go around and set it up. But if you have rooms on either opposite sides, you can do more than one room if they're not communicating with each other from a static pressure standpoint. So looking at as far as the clean rooms, as far as what's acceptable, I'm not so sure I have the slide in this. I know I have my other presentation. What is acceptable differential during the modulation process? And typically we're saying 20%. That's what we agreed on in the NIP committee. So, but now realize that's not much pressure. So you're talking about going from, if you have a differential of say 25 pascals, you're talking, 20% of that. So 5 pascals, that's pretty tight. So you really don't want to be modulating two spaces next that communicate each other from a static pressure standpoint at the same time, because you may end up losing that pressure relationship. You got to think about the speed of actuation. Typically, they go high speed because you get as much modulation as you want out of it. Alarm points, that's what you work with your client. When do you want to alarm? What's alert? What's alarm points that you want to set on that? So you got to think about that. Okay, so here we're going to look at the economics, and I'm looking at 3 ways here. So the worst cases is what I showed there, as far as what I'm doing at EI Lilly, where we're set and forget. We put these Venturi valves in, we set them, we forget them, we walk away. The next option is we're looking at is that, okay, we have airflow sensors in there, and we have modulating dampers in there, and so that's because that was a requirement of the project. The third option is that we have this, but in that particular case, the second case, we're going with the in-room particulate measuring sensors. Then we're just going to go on the third option is instead of using the in-room particulate sensor, we're going to go with the sequencing. So for the first one that's set and forget, this is what you have to add to that. You have to provide supplier damper, return air damper, exhaust air sensors rather, supplier modulation actuators, return air modulation. If you don't have space differential pressure sensors, you got to install that. The particulate measuring sensors, the whole system, and obviously you got to develop the sequence of operation. So I threw some cost in here. This is US dollars. And so it gives you a feel for each one, and the vacuum pump's a variable because it's all based upon how much your vacuum is. So what I did here is I showed it as far as for 3 spaces, and then this is for 6 spaces. So as you can see, the cost goes up nicely. So what I did is I put costs together as far as single space, original set, and forget. So for single space, you can get up to $126,000 for single space just for getting this thing to a point where it's a set and forget. From set and forget to being a control. For 3 spaces, it's up to 340,000. For 6 spaces, it can get up to almost $750,000. If you want to implement this, if you're starting with the set and forget. Now let's look at the second one, which is that you have a lot of the infrastructure in there and you are measuring in the room. So quickly, as you can see, it's a little cheaper and it gets up to about 591,000. So we're saving a little money, but it's still not the greatest. So let's look at it from using a sequencer, a lot cheaper. So we get down to where if we went from about 660,000 down to 380 using a sequencer. This is for 6 spaces. So this is much more, and because you are going to operate do the rooms one at a time, then they're connected pressure differentially, this is a much better option to go with. All right, so let's look at I'll go through these relatively quick. I don't know what my time is right now.
5 minutes.
Huh?
5 minutes.
Oh, 5 minutes. Oh, I'm doing good. Blind squirrel finds a nut on occasion. So anyways, so looking at, we know what cost is. Now, what is our return? What is our payback, simple payback on this? So looking at it for the single space, I put in, sorry, the square foot, but I put 20 air changes for an ISO 8, 50 for 7, and an ISO 5, 300 air changes. So if you look at the simple payback for those 3 items, now this is just for a single space now, and this is the worst condition where we have to provide all the infrastructure. Well, look under ISO 5, it has less than 5-year payback for all sizes of cleaners for a single room. And if you look at a lot of them, is less than 2 years. Now this is the worst condition. This is the absolute worst. And look at, you get some really nice paybacks for a single room on an ISO 5. Now on an ISO, I didn't put ISO 6 in because it's an odd ISO class. I only done a couple where I've had an ISO 6. So I looked that out. I did the 3 most prevalent. And I put anything over 5 to 8 air chain here. So if you do an evaluation, it may be worth even for an ISO 7. And this is single space. So this is the worst you're going to see. Going through as far as for 3 spaces, you can get a little more in the ISO 7. For the 6 spaces, you can see now you got paybacks less than a year. And that's with the worst condition where we have to provide all that infrastructure. So what happened there? Yeah, what happened? Oh, there you go. Thank you. Okay, so now let's look at it as far as the next one. Is that the same one? Oh no, this is here we go. So this is the second one where we do have a lot of the infrastructure provided already, and we're still using the particulate measuring inside the space. Again, we're looking good as far as the ISO 5s and cleaner, look fantastic. ISO 7s, depending on the number of spaces, is looking good as well. So it's looks pretty good. Now we get into the 6 spaces. Again, the ISO 5 and cleaner it's very attractive. The ISO 7s are even looking more attractive as well. So let's go further. There we go. And let's use the sequencer. So let's look at that. Right away, as far as the sequencer, for a single space, obviously the ISO 5, that's the theme here. The ISO 7s even become more attractive because of the cost savings. You know, we went from that 600 and some odd thousand for 6 rooms down to 381. So it was a huge savings. Now we're at 3 spaces, and as you can tell, we're even get to a point where maybe even an ISO 8 room may even be attractive to implement. And looking at it for the 6 spaces, you can see, look at that, you got paybacks of less than a half year. So there's some huge advantages to implement it. So looking at demand-based ventilation, if it's an ISO 5 or cleaner, so that's 1, 2, 3, 4, 5, absolutely it is the numbers, regardless of which way you go with it. If you're going to existing facility and it's a set and forget and you're modifying it to have demand control ventilation, there's a lot of advantages to doing it as far as energy savings. You know, looking at specific situations for ISO 6 and 7, I think that 6 is probably going to be very attractive as well. I think ISO 7 showed a fair amount that if you got more spaces, tends to be very attractive as well. So I think you need to look at that as far as those and do an analysis in those. I'm a little hesitant on the ISO 8 spaces at this point. You could do an analysis, but as you can see from what I can provide it's going to be tough to make it economically viable. And with that, thank you.
Thank you, Vince. That was fantastic. Really interesting. Next up, we have Wei Sun is as our next distinguished lecturer. I bring this with me because if I was to actually give everything that Wei has contributed to ASHRAE, I think I would need to actually add another section to today's proceedings. So Wei has been Wei in his day job is a president of
Cisco.
And Cisco, thank you for saying that. In Ann Arbor, in Michigan, that's his day job. But in ASHRAE, he has been the chair of TC 911. They're taken over, but also TC 9.6, which is healthcare facilities, and TC 910, which is lab systems. He is the regional vice chair or has been the regional vice chair for ASHRAE Region 5 and president of ASHRAE Detroit chapter. He's served as president of the IEST, the Institute of Environmental Science and Technology in Chicago, and he's also the delegate, the USA delegate for 14644, and sits on the NEBB as well. And also, actually, an important point, he has committed, given so much of his time, he has received both the ASHRAE Distinguished Lecturer, Distinguished Service Award and the Exceptional Services Award. So, hand you over to Wei. Thank you. So what we'll do is just update on proceedings. Wei, you'll speak for about half hour or so.
Half an hour.
Yeah, that'll just bring us just beyond 6 o'clock, and then we'll have some questions. Okay to stick around for 6:15?
Okay.
Cool. Thank you.
Well, thank Howard for your very nice introduction, and it's my great honor to be invited to participate in this event. And this is my second time as DL to this great chapter. And one thing I noticed, some people ask me, what's the difference between my last visit and this visit? I said, well, on highway, I noticed you have more new buildings looks like more prosperous and more opportunities. So since you're giving me 30 minutes, I'm going to start my topic. The agenda I have basically is talking about the control environments. And a few things we like to talk about is the coordinate control. And the second is the contaminant control strategy. And quarter is the expertise. Third is the pressurization. And also talk about some examples, airlocks, and also AHO diagram. And also very quick on the application. This used to be actually 3 of my DL topics. I squeezed them into one. And now I try to do my best on 45 minutes to be 30 minutes. So cover on the healthcare, laboratory, and the clean rooms. And so for part one, we talk about the indoor environment under the coordinate control. For commercial space, for space like this, we have temperature, humidity, airflow, supply return, exhaust, some other control conditions. So let's look for the commercial space, airflow, temperature, sometimes humidity, and we also sometimes maybe airflow pattern, but most of the time may not. And we also have a project specifics, sound vibration, lighting, etc. These are very common for virtually all buildings design. As you outline on your right side, these are we call the control environments. My career actually studying designing the commercial spaces, then moved to healthcare. I did a good job, then moved to the laboratory. So okay, since clean room is maybe one of the most complicated, then put me on that side. So if we look at the healthcare, we have temperature, humidity, airflow, and room pressure. And of course, for the conventional project specifics, sometimes we have a microbial contamination concern, especially for operating room, isolation room, sometimes maybe for intensive care, and sometimes maybe the ISO class or GMP grade, especially for operating room. We design for ISO 7 or 8, but we do not test for that. So in the US, there is some kind of, operating room is a clean room, but it's not tested as a clean room. Now, international codes in different countries could change. Some other countries may require to test operating room as clean room, as long as it identifies ISO 8 or ISO 7. For laboratory, you have many control conditions, but in addition, you have a chemical film, vapor, and a gas phase contaminations. And you have a microbial, especially for biosafety laboratories. And for clean rooms, which we have everything. And also you have the ISO class and GMP grade requirement. And you have an electrostatic discharge. So make it more complicated. One thing I'd like to mention is that many of these variables are mutually correlated. For example, if you modulate the airflow, it could impact the room airflow pattern, room pressure, particle concentration or contaminant concentration instantaneously. And gradually, maybe within a few minutes, you'll impact the temperature, humidity. So control of a clean room's condition is much more complicated and complex than the commercial space. So that's why the control environment is much more complicated, especially for the clean rooms. And I like to put this contaminant control strategy in 2 categories. One is within the room, the other is between the rooms. So within the room, we have a source control. Let me see if I can. Yeah, first is the reduction, isolation, and the removal of the contaminant source strains. Reduction is you try to emit as low as can. Isolation, you put a gun in, that's the isolation. Removal is you have a snorkel, exhaust or other means. If you have a high concentration locations, you want to remove them locally as fast as you can. However, if all this you have done, then the only thing remaining you can do to lower the concentration is through the dilution and the displacement. Now, dilution and displacement is a very expensive measure. It's much easier and cost effective to do this first, but some contaminant will escape and disperse into the room. Then you use the dilution and the displacement. Typically for use a HEPA filter or filtered supply air, and through effective passages for contaminant exit. For the control environments, people typically look at the ceiling level, have HEPA, have a FFU, but they pay less attention on the contaminant exit. So if I consider this room as a control environment, I call this like a fish tank. You have fishes, generate waste. You have clean water, you pump in, you drink the same amount of water out. So the water level stay the same. But if you drink not at the dirtiest location, but in somewhere at a high position, you still drink the same amount of water, but you do not take down the contaminants. If you do not take down the contaminants, the concentration of the water in terms of the contamination will move high, will be getting dirtier and dirtier. So it's not about how much air you take it on. It's about if you take it on the air, you take on as much as contaminants, which are generally within the space. So that's very critical. I call it a fish tank scenario. And another within the inside the space is the transmission control with distancing during COVID. And the other thing is airflow cascade. I'm going to talk about more for the rest of the slides. Between the room, we use pressurization and depressurization. Now, pressurization, depressurization is only good if all the doors close. If you leave a door open, if a little gap, you do not have a dead up here. I learned this from Dr. Cover when I was a student many years ago. And the other thing is pressurization is a static pressure control. I call it particle migration control. But since you have a door, you're going to use a door for traffic, personnel, material, products, or waste. Airlock is a dynamic control. So you have a static control and a dynamic control, all this in the category of migration control between the room, from the clean room and outside or from the lab. The other thing I like to put into the presentation is the, I call it protected area and a contaminated area. Let's look at the commercial spaces first. We have a protected area, we have a contaminated area. Typically, they do not have a buffer zone between. Stairwell, we pressurize the stairwell as the passage for egress. So the stairwell has a higher pressure than the surrounding. So the stairway is a protected area. The rest building typically has lower pressure. So one high, one low. For kitchen, it's a reverse. Kitchen is generally older. So typically has a lower pressure than the dining area and the rest building. For the restroom, if people know, you want to tolerate some exhaust. More air on, less air in, so lower than the pressure across the door. For commercial spaces, they do not have a buffer zone. So the door is the only barrier to separate these two zones. Now, for control environments, the difference is they have a buffer zone. For clean room, typically you pressurize it, so the hallway has a low pressure. You want to make sure contaminant in a hallway will not migrate into the clean room. For the lab, it's the other way. Lab room is a contaminated area. So it's a lower pressure. The corridor is a high pressure, but if you design corridor in neutral pressure, typically this is a negative pressure. And the airlock, most time being used, especially for by safety laboratory level 3, 4. And in healthcare, operating room, surgical room is the protected area. The hallway, the corridor is the lower pressure. between them, there should be empty room. For the isolation room, in the healthcare industry, the patient room is highly contaminated. The corridor is that the potential area you do not want to have contaminated migrate into the corridor. So empty room is a buffer zone. We need to talk about pressurization. So I try to illustrate in a simple way. If you have some incoming air, typically supply air, more than departing air, typically return air and exhaust air combined, more in, less out, the room is pressurized. If in and out in an equivalent level, they have a similar pressure as the surrounding. If you have a less in, more out, the room is depressurized. So for pressurized room, you basically have air surplus. So you squeeze the air on through the undesignated leakage cracks or openings. In the depressurization, because you have a deficit, you have a shortage. So you actively draw the air from surrounding space through the cracks to compensate the difference. So this is what is the easy way to talk about. Now, how much pressure, how tight of the air, what's the air tightness of the space, that's another 2-hour topic. So, but if you type in ASHRAE journal, type in the pressurization of my name, you find some article for that. Now we talk about the dynamic contaminant migration control, airlock, as we talked about earlier. Typically, there was 4 types: cascading, bubble, sink, and a deep compartment. Cascading is the room has a high pressure than the corridor. So airlock is in the somewhere between. Bubble is the airlock has a higher pressure, higher than corridor, higher than the room. Sink is the other way, the lowest pressure. And deep compartment is you put a sink and a bubble in series. So if you want to walk from the hallway into let's say a clean room, you're going to walk through the first door, second door, and then third door, because during the egress, you always can push it around for exit. So, so these are very common 4 types, especially for the clean room. In other, in laboratory or healthcare, they use an empty room. But, so let's look at your one example. Transmission control by airflow cascade. If the process is not harmful to personnel, let's say if you want to pretend the process, you put your upstream, which is the filtered air, and you put the midstream, which is your process, you put a personnel is a downstream. So this is based on the assumption that the process itself is not harmful to personnel. Now, sometimes process could be harmful. So if it is harmful and you want to pretend the personnel and the room, so upstream, filtered air, midstream, personnel. And you put a process in the downstream. So that's the difference between the first scenario, first and the second scenarios. The first is a process in midstream, but the second is the personnel is in the midstream, and you put a process in downstream. And so if you want to pretend the personnel, process, and the room all together, and you know the process is harmful to personnel, could be toxic, could be infectious or others, so we call it harmful. And so let's look at this illustration. Upstream, filtered air, midstream, process. And so you have captured or enclosed the process, make sure you take much contaminant as possible. And you put a personnel in an enclosed environment with a little small opening. Typically, let's say if laboratory is a such film called such opening, you give a little spaces so you can put hands in, or you have a glove box. You have indirect connections. So that's the way. That's the way to simply illustrate the airflow cascade concept for the control environment. For AHRAE diagram, let's say for this very common diagram, I list many options that you never use all these options in a single project, but I put them together just for illustration purpose. You have an on-site air, pass through heating cooling coils, sometimes humidification, sometimes reheat. Of course, definitely have filters. And the supply fan pump the air, chew the air into the space. The return fan draw the air from the space. And you can pass through the first return or second return, or sometime, let me see this first. If you have, especially for control environment, especially by safety laboratory, sometimes the air being contaminated, you want to purge the air out. You want to purge the old air out before you maintain air conditioning or temperature, humidity, or room pressure. To do that, of course, you can draw on-site air, pass through many coils, but also you can just bring on-site air if the on-site air conditioning is not going to cause you freezing or condensation. If in summer, you can bring the filtered on-site air, use a supply air, pump into the space, and use the return fan. You shut off the return air pass damper, shut off the exhaust. So this return fan can serve as a purge exhaust fan. And so during the normal time, you can use the first return, second return, and the percentage assigned percentage, if there's a one, let's say 30, the other 70, but the total is 100%. The rule of that is for your sequence operation is that based on the indoor condition and based on outdoor condition, you want to use the minimized mechanical heating or cooling. You create a situation so your control algorithm going to have a certain percentage assignment. It is dynamic. It's not like a fixed. It's a dynamic control by the computer. And also, you also can, of course, entropy wheel if there is no contamination. Entropy wheel has a little leakage over there. So if there is if the return air is not so dirty, you can recover some energy. And some other time, and you can use the evaporate cooling. Let's say use a heat pipe to recover. Let's say if the room temperature, let's say 75 degrees, by air spraying, you reduce the air temperature downstream. Then you recover with a heat pipe, so you can pre-cool the return temperature to minimize the energy consumption. Because return air, you exhaust them out, you kind of waste a lot of energy. Return air has been treated, either cooled or heated. So you can get some energy back through the heat pipe recovery with this. So in this illustration, you can use the exhaust only. You can use the exhaust with heat pipe. You can use exhaust with the entropy wheel. You can use a dual return. You can use 100% on-site air for purge. But in no single case, you use all these options in a single project. It just, it's all the possibility. And you're going to design for summer condition, winter condition, occupied condition, unoccupied, and anywhere between. So your control algorithm or reset schedule need to be capable enough to make sure anytime in a typical year, you have all these control logics covered. And since I have limited time, actually did a epidemic task force, and this is the website. You click any of these icon, actually, or button, you have a detailed information and publications are and available. Second part, let me get some water. I'm sorry. Thank you. Thank you. The second part is a very quick illustration regarding the application, starting with the healthcare first. Typically, first of all, we use the PPE as a primary barrier our HVAC design, we call it engineering control, actually is the secondary barrier. And on the secondary barrier, patient placement, like room layout configuration, and also space environmental control. So for many of our ASHRAE members, this is our focus. And based on US CDC, these are the 4 major categories for the infectious control space: operating room, isolation room, planetary environment, intensive critical care. And I use the USA for example. In USA, we have multiple guidelines and standards. ASHRAE is one, CDC one, AI, not critical FGI, and many others. For example, VA hospital, they have their own guidelines. So, but these 3 are the most commonly utilized. So typically we pick one of the most stringent. Once you cover the most stringent, you cover the rest. And so the pressure relationship to the adjacent area, this is one of the most complicated. Temperature, humidity, a little bit easier. Air change rate, and based on the standard, you can set up through your control. And isolation anteroom.
There you go, back. So, hi, welcome back to Oliver online. Just had a little bit of a glitch here on the Wi-Fi, so hopefully you're back listening to us, are you? Gives an L thumbs up. It gives an L thumbs up if you can hear us.
Yes, back, thanks.
Oh, thanks, Ethan.
Yeah, thank you. Thank you for the very short break.
Short break.
For operating room, style design in the US, typically sometimes people use the linear diffuser. They put HEPA filters on the downstream, at the downstream of AHU, then duct it to the space above and create some kind of linear or air curtain type. But now it's more common, people just use the HEPA cover above the surgical beds. And this is a CDC diagram. And the more advanced design right now, especially for some European countries, in US, based on our ASHRAE 170, if this is a surgical bed, our HEPA coverage only need to be 12-inch wider, 1 foot wider. Anything with that size, it considers okay. But lots of European design, you use a 3 meter by 3 meters. And I'm not talking all the European countries, but many. And in US, we talk about air change per hour, 20, 25, maybe in that range. Lots of other European standards use the high air change per hour, and sometimes use the air curtain. This curtain can use it's motorized. You can drop or can flush to the ceiling, so it provides a more guided vertical down unidirectional. Because what happened is, in a typical operating room, in orders, we use a very high kW for surgical lights, so they create a buoyancy. Even you have a very strong 90 feet per minute HEPA airflow downward, because of the buoyancy, they still cause some kind of reverse airflow. But nowadays, surgical lights use LED, but if you have a little high ceiling, physical vertical curtain down could be helpful. This is the difference I'm trying to talk about. If you have a 1 room AHU, let's say 700 CFM, which is roughly about 20 air change per hour to the room. But in the room, you can create a 40 or 60 air change per hour. Not increase the size of AHU, but to utilize the fan filter unit to create a more recirculation and to achieve a bigger HEPA coverage above the surgical bed and also provide a stronger velocity for that. And so this is the concept we call a primary secondary flow. One is for recirculation, the other is for the AHU airflow. And this is a typical concept for the clean room design. But for healthcare design, there is a trend from 100% air from AHU to be air from AHU plus the recirculation air in order to enhance the air change per hour into the space. So that's the potential environment. I try to move quick. Typically design positive pressure, and based on US CDC. Now US CDC is the minimum. Some other standard could be more stringent. Some customer may ask for more stringent design, but I use the US CDC as a minimum. So for their guideline, they're saying you need to have a 125 CFM more for air in than air out. And they also put the minimum maximum leakage area. I thought Carl is an expert. Equivalent leakage area on the 4-pascal, and some photos and a very simple diagram. And the critical and the intensive care are typically positive, and the data is a little bit lower, but they do not need to have a HEPA. About 90% efficiency or higher will be okay, and recirculation is allowed. Now, for the operating room, based on US standard, the recirculation is allowed. Many other country standard, they want to use 100% on-site air. So each country have a slightly different standard. But for critical intensive care, definitely is the low end. So recirculation is allowed. Some photos. And now the most stringent and complicated in healthcare setting is isolation room. And it is an inactive pressure and have a leakage requirement. And also the supply air need to be filtered 90% higher. The exhaust air need to be HEPA filtered. And recirculation is not allowed. Sidewall return behind the bed wall. And UVGI feature can be placed, and also plus the identity gears. And personally, I have this during the COVID. Actually, we use it for testing purpose, but I have this. So sometimes walk to some facility and say, how much cost for this? But for the isolation room, this is based on the US CDC. The anteroom, which is airlock room, have a different style. One is cascading. Airflow is like a one-way, always higher than anteroom, which is higher than the patient room, and the rest room is the lowest. So it's a one-way. Or you can use the bubble, and or you can use a sink. So based on US CDC, these are the 3 types of the anteroom configuration. And once again, I have a 2 hours talk just for that. But I'm going to. Now, the second, I'm talking about the laboratory. First is we call a hazard assessment. Could be chemical, could be radiation, could be biological, fire loss, and many process specifics. Now, for laboratory design in the US, sometimes we based on the building column spacing. We provide, let's say, become more commonly we call a flexible modular concept. So based on the spacing, you can have the, let's say, single module. If a new faculty give us space, you give a 1/3 or 2/3. Or some, you have lots of research activity or process, you give a double module. So basically, is based on the columns of a building spacing, you can divide it into multiple configuration. In case some need to change it, they just remove the partition and and so some flexibility. And one thing for lavatory is feature is the we call the fume hoods. Sometimes fume hoods, sometimes by safety cabinets. You can have a bench top. You can have a walk-in, and for fume hood, you have a constant exhaust. You can have a bypass, restricted bypass, auxiliary. But nowadays, more common for VAV, use a restrictive bypass. And when the sash is open, sash opening is the main air into the fume hood and exhaust. When the sash is closed, in the front louver, they draw some air. In the bottom, they draw some air. So to maintain a low exhaust, because the fume hood inside could constantly generate some fumes, even if it's not in use. And customized hood, this is similar like we in the supermarket displays cases. But this is a harmful activity inside. So do not open the door without authorization. And exhaust, in old days, people use an individual fan, exhaust fan for one hood, but non-commonly is more use a manifold, multiple, even use a variable speed, variable frequency for exhaust. And the face velocity, in US, multiple organizations have the such opening face velocity requirements. So typically for the 80 to 100 feet, we pretty much meet all these requirements. And the other thing is we have a chemical labs, radiation labs or whatever, but also another very important category is by safety cabinets. And based on US definition, you have a class 1, class 2, class 3. In class 2, you have A, you have B1, B2, B3, and the face velocity requirement, airflow pattern requirement, and application requirement. So I believe you have a PDF. So and some by safety internal structure design. So I think I'm going to skip this. And the point I try to make is most of these fume hood by safety cabinets, they have air exchange with the room. So when you do a room pressurization or pressure control, you make sure air going to be balanced in a dynamic way. Because you move the sash hood or you change the exhaust volume a certain way, you may impact the room pressure. So the design of this laboratory is not just the room alone, and also the interaction with these hoods or by safety cabinets. So I'm going to skip this. In addition to the by safety cabinets, you have a by safety laboratory. So 1, 2, 3, 4. So I'm going to move quick. Level 3, level 4. So some example for the floor plans. Level 3, level 4. Typically, we call a boxing box design. So it's a slow cured concrete. It's a very low leakage level and pressurized too. And 3 typically respirator. 4 is a pressurizer. We call a bubble suit. And so I'm going to move very quick. Airtight airlock, by safety door. Safety door we call a submarine door in a cheaper version. And some labs in the university for labs. And so apologize, I need 5 more minutes. I need to cover the clean rooms.
Okay.
So clean room by ISO definition, particle size, ISO clean class, and a maximum concentration. So this is a better visualization than a table illustration. Yeah, for pattern, unidirectional, conventional, unidirectional, mixed flow, and mini environment. And this is specifically for semiconductor facility. We call it fan filter unit configuration. Clean room floor, room level below is a return air, and below typically we house process equipment. And above the ceiling is you put the fan filter units on it. And this IESD table before 2014. ISO class, these are the recommended change per hour range, but there is no really scientific justification. But in old days, you try to meet the ISO air cleanliness first. then concern about the energy conservation later, but now as Vincent talked about, energy consumption is a major consideration. As Dr. Colliver mentioned, typically for clean rooms is if you feature more particles, you typically need to have more air to dilute or displace. And so one thing is for low-end clean rooms, ISO 8 and 9, typically the air configuration, ASHRAE configuration is very similar as for commercial space. ASHRAE, outside air, return air, and pass through HEPA filter. So in the space, you have a particle generation, you have exhaust, you have a particle deposition, then you pressurize, you have leakage air, and then you have an average particle concentration in the space. Now for the high end, ISO 7 and a cleaner, it's very similar, but you add another loop, air loop. This loop is for air recirculation. So as such, your air change per hour or total CFM into the space is several times more. So you notice this fan actually much bigger than that fan. So this could be 5 times more or maybe 20 times more. And this I use one fan, but it typically is a group of fan filter units. So we have multiple fans in parallel relationship, you pump air down, that's how you achieve several hundred air change per hour. And as such, your room average concentration drastically reduced because you add a lot of air in, and all this air not really in through the air tube, but through a recirculation system. So, so I'm going to move very quick on this. I was knocking here. Looks like I have 1 more minute. So I'm going to put this first. Then have a very quick discussion. Okay. Okay. Here's this. So for clean room, typically we design for temperature, humidity, but clean room you may have a critical process. Sometimes could be in a chamber, mini environment, or so you have a hood. You can put wraps, which is a restricted access barrier, and an isolator by safety cabinets, mini environment. So within this small chamber or space, you have temperature, humidity, and particle concern, and a unit designed by manufacturer. In the space, you have people, you have machinery, and they generate particles. And particles into the clean room, so impact the cleanness, and also in the room, you have room supply air down. So you have air velocity, pattern, air change rate, and a contaminant removal effectiveness. And also for clean room, there is a recovery time concept. So, and as a HEPA FFU to provide air to the space. And in the room, you have a supply air, you have return exhaust air, and between this air stream difference, you have the room pressure. And room pressure will decide during the door opening operation, how much particle going to migrate from clean room to on-site. But if you do not have a good data peak control, particle can move into the clean room. And so eventually will impact the room air cleanliness. So clean room air cleanliness is an outcome of multiple variables and much more complicated than a commercial space design. You focus on the room alone, and they are going to focus on the containment devices, meeting environment, a lot of other things, the room pressure, many other things. So make the clean design more complicated, and they are mutually, all these variables are mutually impact. So I believe some photos, ISO 5 for semiconductor, ISO 3. So this is for the pharma filling station, and ISO 7 hallway, and a mini environment, aerospace simulation, and this lab for clean room research actually is my lab, similar as a John's, but it's a different. Vincent talked about manifold, sequential, right? And this is our aerosol emission generation delivery system. And so we have a control algorithm, but this is just a quick illustration. So I think my time is.
Yes, I think we would love to. Great, and we're just
Okay.
going to quick questions. So what I'm going to suggest, do we have any questions online?
First of all,
If you want to jump in there. Don't jump in here, up here for a second, pull your chair with you as well. And, yeah, there you go.
Haven't had any questions.
Okay.
Well, just can we get a copy of the presentation?
Yes, of course, yeah. What we do is we'll stick the, so if you want to jump in there, wait for a second.
Sure.
We'll just take a couple of questions from the room anyway. If we can, there we go. Feel free to pull in here. We'll jump into that, I'm sure there.
Oh,
Yeah.
okay.
Yeah.
Okay. I'll still be the bodyguard for both of you.
Yeah.
We are a little bit closer now, but we have a few more minutes, I'm sure, but, do you all have a question or two from the room for the board? Oh.
Vincent, isn't it?
Yes.
On the energy one, you showed up the ISO grades and how you were able to save all the energy. But was it only particles you were measuring, or were you looking at the micro side? Was it or any of those facilities GMP? So that you were able to prove that when you drop the air volume or whatever, hold it down for, that you were achieving particles and the microbial, or were there limits? Not the particles?
Didn't do that for a GMP facility, because again, that'd be FDA regulated as far as air change rates.
And the big thing I took out of it anyway, what you said was, you gotta do this right, you need to have the drops per room.
Yeah.
Because you don't have the drops per room, it's gonna be very difficult.
Yeah, you can't control it.
Yeah.
Yeah. You have to do airflow, because I remember talking to someone about that before, and they're saying, well, we have this pressure differential sensor. The problem with the doing it by just the pressure differential sensor, not your volumetric offset, is that, you know, if I showed you the setup seminar I did in Athens, Greece, and that one, then you say, oh, there's no way to do it unless you have the actual air volumes involved.
Yeah,
And you have to be able to, you have to measure air.
That would be- And just on the device with all the tubing coming into it, what you saw there.
The sequential one?
Yeah.
Yeah,
Connor has educated me over the years, and he's told me about the problems with tubing and lengths of tubing and losses in tubing and false readings with tubing.
we just voted on which section part was that as far as the included,
H3.
that had the length?
No, it's the TR, which is a technical report,
Yeah,
-21.
I think it's 2 meters. Is it?
Well, the TR talks about because, well, if you go to Annex 1, there's clause 5.9, which says the tube length should be less than 1 meter with the minimum of bends. So the TR report gives you a table to go through it, where it's less than 1 meter, greater than, and probably over 3. You do additional measurements of comparisons with no tubing versus the configuration.
Right,
But it's really around the particle size, because this particle size around 5 microns can get caught up in the tubing and the bends. So the variables are the length of tubing, the number of bends, the tube diameter,
Mhm.
and also the surface roughness inside the tube. So the technical report gives you all the various considerations
Mhm.
to take that into account. So obviously the downside of a manifold system is that you run the risk of capturing larger particles and it's retained in the tubing.
Right,
And then they're released at a certain point, and then they're collected.
so you can
And
get false
agglomerated.
readings
You
then.
get
Yeah.
false readings.
So that was,
But the way you've done.
Yeah, I can add a little bit regarding the length of the tubing. There is two different two categories. One is if you connect to the particle counter directory, there is a length requirement, and also the radius you can go certain size. In US, typically about 7-inch. You don't want to have a small band. You want to have a large loop. The other is the tubing regarding manifold. Manifold by most manufacturers, you can go up to about 125 feet. So they designed with a long distance, but they have a purchase cycle inside, like Vincent talking about. Typically, you have a sampling time, you have a tear time, which is a kind of flush the tubing before you take a reading after. So if you have 16 channels, 20 seconds for sampling, 15 seconds for tear time, so 35 seconds. So if you have 16 channel, you roughly are going to wait for 9.3 minutes. But if you change the setting, could be even shorter or longer, but this by manufacturer by default. But tubing have issues. Even you have flush cycle there, they still have some residuals. So what we found is for the tubing system, compared with the laser particle counter or sensor at the same time, same spot, tubing system always, it's not going to that high, it's not going to that low, it's kind of being tempered. So in some cases, their reading may not be as accurate as the space measure. And so for certain industry, they use a tubing as monitoring. But for your certification, ISO by ISO or by NBB, they use the in space measurement as the key data for certification. And also Vincent talked about the feedback control for variable flow. And you can have the average particle sensor reading as the ISO classification. And sometimes we put the sensor at the common return duct to compare what's the difference between these two. And return duct, of course, they being drastically tempered. So the reading is not that high and not that low, and there was a time delay as well. So I think I overextend the question.
No, you're good.
Online people here.
Yes, I think so, yes.
It's on battery. It's battery.
Okay, that's fine. So Dave, sorry, I saw the chat line there as well.
Yeah, just another question.
Just want to make sure now
Yeah,
that people can hear online. I was just worried when I saw it there, so they're not hearing.
No, it's like the charging line, it's okay.
Okay, so, but remember, the manifold system, if you got a purge, the risk is you lose particles in the system that are then purged, up to 50% on larger particles. So on a GMP facility will not allow a manifold system.
Yeah, I'm trying to stay away from it. This is what I've been told.
If for non-critical, it could be used as monitoring because it provides some data. But for control or certification purpose, it's better use a particle counter as the major source of your concentration readings.
Okay.
And yeah.
So
And that's one of the reasons why in my presentation, I presented it as far as with the particle counters in the space. And then with the sequential, even though the sequential is economically more viable, you know, as far as being able to get that through, the problem is and I agree with Connor 100% is the fact, because I've always been against it because of the tubing, and as far as you get particle capture, and then you can release also, and it could be something such as relative, if you don't maintain relative humidity properly in the space, well, the air flowing through there, you're going to get some electrostatic, and you're going to capture particles. Then the first time you get a nice day, then it releases, and you're going to get a false reading. So that's just something to think about. I agree, it's very complex. That's why I show both. Because if you want to bite that apple, the sequential, you got to understand the complexity behind it.
So I'm looking at this question there from Edith. John.
I just want to ask that one there. So Don's last slide mentioned stretching codes. Is this something that will be considered by a client as it could impact certification at completion? And does it come down to how standard operating procedures are written in relation to allowing for setbacks?
Okay, I was reading that.
A lot of questions in there.
I was reading that.
Is that your slide, Don?
So at the end, I was talking about as we look at energy efficiency, as we look at decarbonization, we're moving our codes. In other words, codes and standards. We're talking about, for instance, energy. We're talking about reducing the amount of energy that's required by buildings. We're talking about and looking at, well, let me give an example. The ASHRAE Advanced Energy Design Guides started out with how can we reduce the energy by 30%. Then we talked about how can we have a whole series of 6 documents there. We then talked about how can we reduce energy by 50%. And now we're going to making buildings net zero energy. And we've got about 700,000 copies of those documents out. So, and those are free, by the way, Advanced Energy Design Guides. I think what we're talking about here is we are taking those documents, and by stretch codes, we're talking about how can we build buildings more energy efficient. And in essence, we're talking about ratcheting up or ratcheting down what the demands are. are what the acceptable limits. Let's take, for instance, the insulation values in a wall. Adding more and more insulation to make the building more energy efficient. When we're talking about stretch codes, we're talking about how can we increase the stringency of the code to achieve what we're actually long-term trying to get to. I don't know how it is in the EU or in Europe, but in America, the code that exists when you submit your building initially is the applicable code. Is that what it is here as well?
It would be at starting, I think, somebody can correct me on this.
Anyway, I guess what
it might not be at planning, it will be at commencement notice.
Okay,
Yeah.
so the moral of the story is that once you start your building, the code, even though the code may change to a more efficient code, you basically you can't change the rules of the game once you've started. And I think that's what that was addressing. I hope that was what was addressing. I wasn't sure. Actually, I was reading that. I wasn't sure exactly what was.
No, I think I know what he is asking is, so if we're stretching the code, so we're saying, probably kind of gets more into what Wade was talking about. So if we're saying, and perhaps what Vince was saying as well. So if we have a code that says, so 14644, which now no longer gives air change rates, isn't that correct?
Yes.
Yes. So, but ultimately, you've got to kind of go to the worst case scenario of code of client's requirements. So I suppose maybe Edith, that's my own view on it, is that it's really about timing. We probably don't have the conversation until much later in the project as to what those actual, how can we push those? Whereas where we probably should be doing is, if you go feasibility, concept, basis of design, basic design, detailed design, IFC. At what point in that timeline can you have these conversations? Because very often, the person who is going to be signing off on this probably isn't involved in the job until somewhere around here, when we really maybe need to be having a conversation with our clients. And I don't know if there are clients on, I think a lot of the names there I see are very much from the design side or from the engineering side. But we need to bring we need, I think, Don, you mentioned this as leaders, we need to be talking to our clients to say, hey, the way that we did it in 1982, and the way we did it in 1992, 2002, doesn't necessarily mean it's the way that we're going to do it in 2032. And that's what we need to be thinking about now. And yes, if just because you wrote down 20 air change rates on a page in 1982, doesn't mean that that's what we have to be doing now, and we should challenge that. Is that the question you're asking, Edith?
What Edith is preparing a response.
Yes, thanks, Howard. That's it. I'm just thinking, yes, if we deviate from what's set in the codes, and I suppose in healthcare we'd say it's a derogation or something like that from the code, and you'd have to have it agreed. But I think in the world of clean rooms, again, to get sign off and for insurance and all of these things, the codes tend to be a bit more stringent. And so how far can you stretch the codes, and is there a risk associated with that?
So if I can just add on that, you have codes. Okay, so you've got statutory requirements and regulatory requirements.
Yes.
Okay, so the standards have moved on. Like Annex 1 does not specify the number of air changes, but you may have codes coming out of the UK NHS on HPNs and HTMs, which may mention things like 20 air changes. But that means they're just out of date and they need to be revised. But we need to distinguish between statutory requirements and regulatory requirements, which are not the same. So in a statutory requirement, you may have a requirement for, say, 5 air changes for ventilation. That's for oxygen replacement, or they may require full fresh air in some areas, right? But I think there's also a lack of understanding of people reading the codes on regulatory requirements. I had a situation last week where somebody said to me, in this pharma application in a hospital, you had to have 100% fresh air. And I said, no, you don't. And they said, yes, you did. And I said, okay, let's open up this is the UK HDM, or I think it was 03 on it. And I said, there you go, research is not insisted on, depending on the application. So you apply risk assessment. So I think we're too much into legacy of doing, well, this is how I did the last job, without actually reading the requirements. So I don't see it being a stretch code. I think the codes give you a minimum. And I think we can do a lot better, but we need to be careful they're not regulated. So I think, Edith, and some of those cases that is opening the document, reading it again, based on what we've done as a legacy. So sometimes we add in risk that's not necessary. We need to be careful of that.
Yeah, another component to that is the staging of when the statutory requirements are at a different time. And I know in America, we've got, the codes are updated every X number of years, but the building codes are not a multiple of that X number of years. So then you get imbalance when one is done 3 years, and the other one's done 5 years. So that's another.
Yeah, I like to use a clean room, for example. For example, Conor and I, we sitting in the ISO standard, and the new standards definitely have a drastic different language as the old one. For example, as Vincent mentioned, demand flow control for clean rooms. Vincent also have a note saying if regulation allows. For pharmaceutical, sometime by now you are not allowed to change the airflow rate. So if you design for this air change, let's say 40 air change per hour, based on the current regulation, looks like you are going to use constant flow until US FDA or other change the language in the standard. But in the healthcare sector, it's also based on which standard you follow. You use a US standard or use some European standard or use a standard in Asia. And even within the states, you have a different organization have their own standards. So as long as you identify what are the standards you are going to comply and follow the most current standards, that's all usually the safe way to do. Yeah. So I'm not sure that the question itself is specifically for certain building type.
I'd like to add just 2 points. One was you mentioned the IEST from 2014, which you gave a table of air change rates. They're gone from the new -4.
Yeah.
So we shouldn't be talking about air change rates. We should.
Yeah, for
Back to
clean
the conversation.
room, IEST, they dropped the air change rate table. And ISO dropped the table. So right now, the table I'm talking about, I specifically say it's before 2014. After that, that table was gone. So you can use it as a guideline, but do not use it as, hey, I need to have this air change per hour because the old standard says so. So just have a little
So the Annex 1 is a PICS document globally of all the regulators, and it does not have any minimum air change rate.
Yes.
Problem is, we are applying legacy issues.
Yeah, we have the tunnel vision. So everyone, I just want to just bring it wrap up. We're a few minutes over time. I especially want to thank our hosts, Dr. McKeown and Dr. Ryan, who have been absolutely fantastic hosts. Amazing facility here. Thank you so very much. Yes, I'm going to thank that they're up next. So I want to thank our sponsors, without whom ASHRAE Ireland would not be able to function. We wouldn't be able to do all the wonderful work that the board do. I want to particularly thank Arcadis, who have helped us as well, but all of our sponsors who have helped us. I want to thank, and of course, our 3 distinguished lecturers, Vincent, Wei, and Don, who have come all the way from America via Athens, and so I'm sure they're all dying to get home to a bit of normality. But thank you so very, very much. It was an incredibly interesting talk, an incredibly interesting tour of the facility here. So thank you all.
Thank you all.
Hey. Thank you all for coming. Thank you all online. We will put the
Yes.
Thank you.
Our president.
Sorry, we're not there in person.
Our president.
Thanks, Edith.
Bye.
We will.